Hello everybody and welcome to the next chapter of our course on basic construction materials. This chapter deals with cement and concrete. Now in most construction sites you will come across concrete. Concrete is probably ubiquitous. It's found all over the world. People are using cement concrete in various different applications. And as I have said in the introductory lecture, concrete is the second most used material in the world or second most consumed material in the world after water. And concrete is made of several different ingredients, that is cement, sand, stone, water, right? And today, of course, we also use some sort of additives which enhance the properties of concrete in fresh and hardened state. So in this chapter, we'll go over the properties of these individual materials and how the composite behaves once you combine these individual materials in a certain fashion, okay? And what are the governing factors responsible for the performance of concrete in real life applications. We'll also look at some concrete construction as to how the process of putting together a concrete structure actually unfolds on a construction site, so that you have some sort of an association with the material and its usage. Okay, so now one basic fact with concrete, as it is true with other construction materials like stone or brick, concrete is very weak in tension. So it is used primarily for compression related applications. That means wherever it can bear compressive loads, it is happy. But as soon as you get tension into concrete, it starts cracking. Okay, so concrete is weak in tension and good in compression. And because of this, we usually combine concrete with steel. Steel is used as a reinforcement for concrete to ensure that you take care of the tensile loads. Okay, so steel basically provides load carrying capacity to the tensile zones. So if you have a beam, for instance, which is bending, when a beam bends, right, let me just draw a beam which is bending, okay. When the beam bends, the bottom is in tension and the top is in compression. So in this case, if the concrete is without any steel, it will start cracking here and the crack will very quickly propagate to the top and your beam will split into two, right. However, when we put in the steel here, as soon as the crack reaches the steel surface, the tensile load is transferred to the steel and the steel basically takes up the tension. Okay? You will learn this concept a lot better when you actually come across the subjects on reinforced concrete design. But essentially, the purpose of the reinforcement is to take away the tension from the concrete. Okay? So, why do we use steel for this purpose? Why can't we use any other metal? For example, aluminum, it's a very good metal. It's got a high strength, it's got much lower weight or density as compared to steel. Why don't we choose aluminum? The main reason is that steel is very well compatible with concrete. Steel and concrete are compatible materials. So steel has nearly the same coefficient of thermal expansion or alpha as concrete. So in case there is a temperature change, the concrete and steel both would expand or contract depending upon whether you have an increase in temperature or a decrease in temperature. Okay. So if they contract or expand at different rates, obviously you'll get incompatibility. So if they have the same rate of thermal expansion or same coefficient of thermal expansion, they will expand at the same rate or contract at the same rate, indicating that you will not get any failures and the composite will be proper. So that's why steel is ideal for concrete, that it has nearly the same coefficient of thermal expansion. But in terms of engineering properties like modulus of elasticity, the two materials are entirely different. And much of the design of reinforced concrete that is done with that kept in mind, that your modulus of steel is much more than the modulus of elasticity of concrete. But nevertheless, they are highly compatible. Steel also provides excellent tensile strength, which is of course provided by many other metals, but they don't have the same compatibility properties with concrete. Further, the concrete basically protects steel from corrosion. So they are mutually helping each other out. Okay? And finally, it's very important to understand that the composite that you produce, the reinforced concrete, behaves in a manner that can take up both compressive and tensile loads. Okay? So steel being good in tension, steel and concrete having the similar coefficient of thermal expansion, these two are the properties that we desire the most, and concrete protects steel from corrosion. Okay, that's another aspect that we talk about. and reinforced concrete becomes very ductile because of the presence of steel. Okay? If steel were not there, concrete will behave in a very brittle fashion. It will break suddenly without any warning. Okay? Now, of course, we know that steel corrodes. Steel will eventually corrode. Okay? Steel has to corrode because the iron in steel wants to get back to its natural state of iron oxide. Okay? Now, what we have to do is design the structure with concrete in such a way that it will protect the steel from corrosion at least until the useful life of the building is over. For example, when you are building a house and you are using reinforced concrete in it, you want to build the house to last you at least your lifetime, right? A typical human being would probably build their house when they are around 40 to 45 years old, right? And assuming you have a good long life up to about 85 to 90 years, that means you have an additional 40 to 50 years to design for, right? So, the house should serve your needs for the next 50 years, and you design your structure in such a way that the steel is protected from corrosion for 50 years by the concrete that surrounds it. Okay? So, both are ideally compatible with each other and both produce an excellent composite that we know as reinforced concrete. Of course, I should also add that steel bonds quite well with concrete. There are other modern reinforcement options that are also available. We will talk about that in the composites, polymers and plastics chapter, like fiber reinforced plastic, where you have fibers embedded in a plastic matrix, and these form very lightweight, excellent tensile strength composites. But there are certain disadvantages about using these. We will talk about that when we actually get to the chapter on composite materials. And meanwhile, of course, my colleague Dr. Pillai will cover the aspect of steel itself, right? Construction with steel as well as steel as a reinforcing material, and the problems of corrosion will be covered by Dr. Pillai. Okay. So, let us proceed with our discussion on cement and concrete. In India, reinforced cement concrete is the most popular construction material. Now, if somebody asks you why is this the case, then you would be able to answer quite clearly that it is probably going to be driven by the economy, right. In most cases, the choice of construction materials depends on what is locally available, what is economical. In India, reinforced concrete is a lot more economical as compared to steel. Okay. Just to give you a comparative cost of materials, your concrete, if you take a cubic meter of concrete, that is nearly about 2500 kilogram. Okay. The cost is probably around let us say 6,000 rupees. Steel on the other hand, usually you measure it in terms of tons. Okay. In tons, the cost is almost about 50,000 rupees per ton. Okay. A ton is 1000 kilograms. So, 1000 kilograms of steel costs you nearly 50,000 rupees, whereas 2500 kilograms of concrete costs you only about 6,000 rupees. So, and this is top of the line concrete. Okay. If you have the options of actually making concrete even cheaper than that. So, concrete is a lot more economical as compared to steel. If you go to job sites, you will also realize that steel construction requires a lot of skill. You need skilled labor to be present to ensure that the steel segments are actually jointed together properly with the right welds, nuts, bolts and rivets and so on. In concrete, you will see that the most basic of functions are going on at the job site. You do not necessarily have people who are well trained. Of course, I am not saying that is actually a good thing. You need to have people who are well trained to ensure that the supervision of the people who are unskilled is proper on the job site. But that does not happen in many of the job sites, and because of which your concrete quality turns out to be poor. Okay. So, concrete requires less skill as compared to steel to operate on a job site. You need less skill to work with the material. It is very easy to work with, it is easy to apply, and then it is economical. And these are the reasons why concrete is much highly preferred as compared to steel. Now, of course, if you think about the time taken for construction, steel construction happens much faster because all the components of the steel construction come from a fabrication in the factory, right? They come to the site and all you need to do is assemble them properly. Concrete on the other hand, in most cases would be made on the site and you need to wait for some time for the concrete to gain strength. We will talk about that a little bit later. Okay? So, in terms of time, steel construction is much faster, but because of that obviously The cost of the materials is high, the time taken is less, so obviously the overall cost of steel construction is going to be much higher than that of concrete construction. Okay, so as a result, you have a preference towards concrete. Okay, now concrete can be supplied and mixed in many ways. It can be either site mixed, that means you are mixing directly on the site, or it can be supplied from a central mixing plant. At least most of you who live in the cities would have seen these ready-mix concrete trucks. Sometimes they are called millers, taking the concrete from the central mixing plants to the job site where the concrete is dispatched or delivered. Okay, so this is a common sight in most urban areas and even rural areas these days, which are in proximity with a good quality concrete plant. Okay. However, of course, in India, most concrete is still site mix because that's an easy operation, right? People are able to do it on their own on the site. So why spend all the money to get a centralized mixing plant concrete, even though it may be better in quality? Of course, that's something we'll talk about a little bit later. In India, the construction is labor intensive, and that's just got to do with the way that the economy works. Okay. In Western countries, if you go to Germany or the US, you'll find that on the job site there are skilled contractors, the skilled not labor, I won't call them laborers, you have skilled workers who are basically operating machinery to make the structure possible. In India, you'll find that there'll be a lot of laborers who work under a team of contractors who can deliver the material to the right place and get the job done. However, there's a major difference between the number of people employed on site in a Western construction site as compared to an Indian construction site. So, just the way that the economy works, we have a large workforce and then they need to be employed, and construction is one of the largest employers as far as India is concerned. After agriculture, construction employs the most number of people. Now, India, of course, we use a lot of volume batching. Now, I'll talk about the benefits and disadvantages of volume batching later, but volume batching is where you simply take materials by volume, and that's something that is quite prevalent in residential construction. You'll see that people are simply mixing based upon measuring quantities by volume. I'll tell you later why that's not such a good thing to do. Anyway, in India, this is how concrete construction happens in residential job sites. When you go to infrastructure, when you go to larger projects, you'll find that there's a much better quality control. People work to make the concrete mix design proper to ensure that the concrete will serve the needs of the infrastructure for many, many years. In residential construction, we don't really have that level of supervision from good quality engineers. Okay, we have mainly contractors who carry out the work, and they definitely do not have the same level of scientific information as the engineers to understand what would happen if the concrete construction is not done properly. Anyway, that's the status of construction in our country. We have to do our bit as engineers to ensure that technical knowledge passes down to the last rung of people who are dealing with the material so that they can understand and apply it on site. Now, of course, this is just an example of building in plain concrete. You see these concrete blocks which have been laid here, okay, and you see this is actually a concrete pavement that has been prepared. Okay, as I said, concrete is excellent in compression, but it's poor in tension. So, the limitations need to be overcome by optimizing the shape or providing reinforcement like steel. So, if you can build with all arches and domes, you don't need any material to take care of the tension, because in arches and domes, the load is entirely transferred by compression. So, in such cases, concrete could be quite useful. For example, if you go to the Pantheon dome in Italy, this Pantheon basically is composed of a dome which is made with waffle-like slabs of concrete, and all the members there are in compression, and there is absolutely no need for a reinforcement there. Okay, so examples are there where plain concrete can be used, but it's quite difficult to construct with plain concrete. So that's why we always construct with reinforced concrete, where steel is embedded in the concrete, and together steel and concrete provide a composite action that takes care of both compression and tension. So here, for example, you have the formwork, right? That is the wooden mold into which you have placed the steel reinforcement. That's your reinforcement that is placed inside. So wooden formwork outside, and then once the steel reinforcement has been completely placed, you will then pour the concrete into this mold. Okay. Again here, this is the process of pouring the concrete from the back of a truck. You see that this is pouring the concrete, and the concrete appears to be quite fluid. So, it is essentially going to be flowing right under the reinforcement, and then you will be subjecting it to processes like vibration or compaction to ensure that it properly envelops the reinforcement, because if you have gaps between concrete and steel in a composite, they will not function together as a composite material. You will have individual functions, and that will not be the right way to go about it. Now, in most modern buildings, at least in the urban areas, you will see that people are following what is known as framed construction, RCC, framed construction. So, here what you see here, you see that the columns, the beams and the slabs are basically coming on top, right. The slab, okay, the columns, beams and the slab, they are all made with reinforced concrete. So, essentially you make up a frame, okay. And as we talked about in the masonry lecture, you can then go about filling up this gap here, which is left behind between the between the columns and the beams. This gap can be filled by masonry infill, okay. You can put masonry infill. As I said, today in modern construction, most common masonry infill that we use is lightweight concrete blocks. Lightweight concrete blocks such as autoclaved aerated concrete or foamed concrete and so on, those can be used for infill walls, okay. So, all you are doing is building up a frame, all the gaps you are plugging with masonry. It could be brick also, okay, it could be brick also, it does not have to be concrete block. Now, in some cases, if you come to more modern type of construction, the wall itself is reinforced concrete, okay. And many of the fast track rapid housing construction projects, you will see that the wall also is reinforced concrete. So, what happens is the entire segment of the wall and the column is cast integrally, and it continues to move up. Your formwork, which is here, continues to move up as you are completing this construction, okay. So, you do not leave behind any gaps, you construct the wall also along with the column, and the wall also is reinforced in this case. In some cases, you have what is called a tunnel form construction. So, you have a tunnel form basically means that a formwork which is shaped like a tunnel, and then you are basically casting concrete all around that formwork, including the walls and the top slab. Everything is cast integrally, okay. So, that is called a tunnel form construction. In a lot of modern apartment buildings, you find that tunnel form concreting has become quite common. And of course, today you can't escape an urban setting without the use of precast concrete, concrete that is prefabricated and brought from factories and simply assembled on site, just like what we do with steel construction, especially with the construction of bridges like the segmental bridges. These are called segmental bridges, okay. What is done is each segment is cast in a factory and is brought to site and assembled on site, okay. So, generally what happens is a precast concrete comes to site and is getting pre-stressed also. We will talk about pre-stressing towards the end of this chapter. So, most of this concrete is pre-stressed. So, for example, just consider a string into which you put one bead, then you put the next bead and so on and so forth, and you are tightening each bead against the next one. Similarly, what you are simply doing here is you have a concrete segment, you bring the next one and the next one and so on, and then you stitch them together with this steel cable that is very strong. You basically push them together to make one composite. That is called a pre-stressed concrete. We will talk about that a little bit later. One of the common things that you observe in many of the multi-storied buildings these days is that they have large open spaces available. They have very large open spaces available, and that enables the creation of large office spaces or malls, for instance, and so on. You have large spacing between the columns. Between columns you have very large spacing, and on the top you see that there are no beams, okay, because the slab itself is functioning like a beam. So, it is called a flat slab concept. Again, something that will that you will learn a little bit later in your curriculum when you take up reinforced concrete design courses, okay. So, pre-stressing, precast concrete are all over the place today with respect to building construction as well as bridge construction. Of course, in the most modern of developments, people are talking about printing concrete. Now, I showed you a picture earlier where the formwork had to be put in place. You need to actually define the shape of the concrete and then put the reinforcement and then place the concrete into it in a more or less liquid form. But what if you are able to simply print the concrete in the shape of the structure that you want? Okay? And that's what is being done with 3D printing, where there are several different manufacturers all across the world who have come up with printers that can actually print concrete. Okay? So what happens in this printing is that you don't need formwork anymore. So you don't need to spend time and money to assemble and disassemble formwork. Instead of that, all you do is wherever you need the material, exactly there you print your material. Now, of course, 3D printing is not a new technology as when you look at other fields, for example, manufacturing or medical technologies. In such cases, 3D printing has been used for quite some time to produce very complex components without actually having to create a mold or a die for them. Okay? So, in construction, however, 3D printing is fairly new, although it's been in research for nearly 10 years now, but application wise, people are talking about it only today. Only for the last 4 or 5 years, there's been a lot of applications with 3D printing around the world. But still, it is a technology that people are experimenting with. So, all you're doing is placing layer by layer the concrete in the location that it is desired. So, you don't need any formwork. So, the structure basically supports itself and hardens and becomes strong. So, again, just to show you an example of how the 3D printing operation can be done. So, on the top left you find a centralized factory where the printing of these components is actually happening. You see here, this nozzle basically is depositing the concrete on in the layers. So, each layer is being deposited separately. Once the layers are printed and the entire wall segment is printed, they are stacked and then cured. The concrete has to be cured or sprayed with water until it gains strength. So, once it's done, you then transport it to the site and then assemble it almost like a masonry structure. Okay? So, this is a prefabricated 3D printed concrete which is brought to site and simply assembled together. However, there are printers which you can actually take to the site and immediately do the construction there. For example, in rough terrains like hills and difficult to reach locations where your normal construction materials and workers cannot be sent, you could think about sending just material with a 3D printer which can actually set up on the ground and simply build around it. And people have been actually thinking about this process for building bases on the moon. Okay? So 3D printing has been thought of as a technology to build bases on the moon. So that's the kind of approach that people are looking at with respect to using 3D printing. At IIT Madras, we have done a fair bit of 3D printing ourselves, and we have actually constructed this India's first 3D printed structure. This is actually just a very small room, but the idea was to print something of the size of a toilet. Okay? Subsequently, we have printed a toilet also and are in the process of printing actually a full-scale house, okay, which will be available on campus. Those of you who visit IIT Madras, I would welcome you to come and see the house that we have printed entirely with 3D printed components. Okay, so having given you this introduction as to how concrete technology is getting adapted and changed, let's now go back to the basics and try to understand what are the different concrete making materials. How is concrete actually prepared from these materials and what are the properties of concrete that make it so unique and so easy to apply on the site. Right, so first and foremost, obviously, we need to understand what concrete is composed of. So, if you think about concrete as a composite material, you can define two phases. One is your cement paste phase, which is a mixture of cement and water, and then you have the aggregate phase, which is composed of coarse and fine aggregate, or in other words, stone and sand. If you go to the original definition of concrete, it will have cement, water, stone and sand. If you made concrete with lime instead of cement, like in the past heritage structures, you would call it lime, water, stone and sand that go into making concrete. Now, how is it different from mortar? In mortar, you don't have any stone. You only have sand, water and the cement or lime. Okay, so that's a mortar. But a concrete is having also the larger pieces of rock thrown in. Okay. Now, we will come to why you need this kind of a composite material in terms of properties of each and every component and how it affects the overall properties of the concrete. However, today of course this is not just the 4 components that you have. You may get additives today that you need to add in the mineral or chemical form. Okay, some minerals like powders, extra powders are usually added to the concrete, or sometimes some chemicals which are there for specific purposes. We will talk about that later. They are added to the concrete to enhance the properties. Okay. So, because of all these inclusions inside concrete, it is a highly heterogeneous material. In the chapter on steel, you will get to see how on a macro level steel looks very highly homogeneous, but on a micro level, because of the different phases that are present, there is some degree of heterogeneity. But in concrete, you can actually see this heterogeneity directly by your naked eye, because the aggregates which you add in concrete are sometimes of the size of 20 millimeters or even more, whereas the paste which is having cement, the cement particles can be a few tens of microns or even smaller than 10 microns in size. So, what is cement? We talked briefly about this in the stone and brick and mortar chapter. Cement is nothing but a binding material. It reacts with water and sets and hardens. Lime does the same thing. However, lime basically reacts with water, pure lime reacts with water to convert to calcium hydroxide and has to absorb carbon dioxide from the atmosphere to convert to calcium carbonate and harden. With time, people found that when they started making lime with impure limestone, they used to get lime that produced high strength. So, they found that this was because of the silica that was present as impurity and the alumina. Okay. So, slowly people started looking at burning impure limestone and producing different types of lime, and later scientists like L.J. Weicat, okay, they prepared the first artificial hydraulic lime by calcining a mixture of limestone, chalk basically, and clay. Okay, this was mixed and then calcined or burnt together, and that gave the first sort of a cement that we have. However, the actual cement that we know today as Portland cement, right, today if you go to any market and buy a cement bag, it will be saying Portland cement. Why did this name come about? It came about because of this person, Joseph Aspdin, in 1824. He obtained a patent for the cement that he actually manufactured. And what did he do? He saw that the cement, after it reacted with water, produced a hardened material that resembled a limestone called Portland limestone in the city of Dorset in United Kingdom. Okay. So, he thought that it looked like that, so let me name it Portland cement. So, he took a patent and named it Portland cement. Okay. Now, the power of this patent, which ran out many years ago, is still such that we call cement as Portland cement everywhere we go. Okay. Today we don't necessarily have to call it Portland cement, but we still call it Portland cement. That's the interesting thing. Okay. So, the invention of cement is credited to Joseph Aspdin, but in reality there were many before him who had actually produced similar types of cement. Okay. Anyway, he got the patent, so his name is associated with invention of cement. Okay. Now, of course, after him, his son basically took over the manufacture of cement and then produced the more modern type of cement as we know it. Okay. Over the years, cement technology has evolved. People have tried to produce cement in much more modern sort of a kiln, modern sort of an operations, and because of that you have much more controlled quality of cement that you actually get in the market today.